So I want to talk about the derivative, and I want to talk about it from the standpoint of the graph, so from an analytical geometric standpoint. And I want to explain, first off, what we mean when we're talking about the derivative, when we talk about a line that's tangential to a certain point on a function. And then I want to talk about the limit definition of the derivative and how we arrive at the limit definition of the derivative, why this calculus makes sense. So I've got the limit definition of the derivative written down here at the bottom, and it's pretty simple. It states that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all of that over h. And I want to talk about how we arrive at this, because it will make sense after we get there, but just looking at it, it doesn't seem to be intuitively true. It doesn't seem to make much sense just from the get-go. So let's go ahead. Let's draw a graph. Okay, we'll draw an x and a y axis here, and so here we go. We've got a y axis here, and we will add an x-axis. Alright, so we have our x and our y. Now, let's draw a function on this graph. Let's say we have this function here, and we're going off to the left and the right. This function is decreasing from negative infinity up to what we'll call point P right here, and then it is increasing from P to positive infinity. And on second thought, I think let's go ahead and not make P what we'll later learn is going to be called our point of concavity here. Let's not do that. Let's go ahead and make P just, so we'll say that it's decreasing from negative infinity to some arbitrary point, and then it increases from that arbitrary point to positive infinity. This is a continuous function. It's smooth. There are no pinch points or anything like that. And the reason I don't want P to be this point right here where the graph changes direction is because once we get to the next step, eventually we're going to draw a line that's tangent to that point on the function, and a line that's tangent to a point on a function in which the function is changing directions, we'll later learn that that point has to be 0, so that's not okay, especially for our purposes here. So I want P to be this point right here, and then I'm going to make another arbitrary point up here called Q. Okay, now P we can just call. We'll have this point right here as x down on the x-axis, and then Q is going to be a point that is x plus the change in x. Now, what does that really mean? Well, just think about it this way: we're moving from x all the way to x plus delta x, and so since we're doing that, that means that we have x, and then we move along some direction, and there's a change in the x value from this point to that point. So let's draw a little line going up from each of these down to the x-axis so we can see what we're looking at. All right. Now, we'll call this right here, over on the left-hand side of things, we'll just call P, from the perspective of a y value, we'll just call it f of x. Okay? And we will call Q up here, but we'll call it f of x, or rather f of x plus delta x, because what is a function really doing? It's saying, well, I'm going to hand you an x value, and if we're doing an f of x, if we're evaluating this function with respect to x, I'm going to say I'm giving you an x value. I want you to plug it into this function, whatever this function is, and then the number that you get out, that's going to be your y value, so you know how to plot a point on the graph based on that. So this is f of x here, corresponding to P, and this is f of x delta x, corresponding to Q. Okay? Now, what is this going to mean for us? Well, we've got these 2 points, P and Q, on our function. We've got our y-axis, we've got our x-axis, and I want to figure out what the slope is of this point right here at P. Well, I can give you an acceptable approximation of this line by drawing what's called a secant line. Now, what we're trying to get, if we want to know the exact slope at point P, then we would need a tangent line. And a tangent line would look a little bit like this. A tangent line is a line that is perfectly tangential to the point P, perfectly tangential to its slope, and there's zero degree of error in understanding its slope. So if we don't know how to do that right off the bat, what if we approximate it? What if we make a secant line, which is going to jump through this function 2 times, and I'm going to make a secant line that passes through point P, but it also just goes up and hits the graph at point Q, which is this arbitrary point that I found earlier. So let's go ahead and let's make a secant line. See if I can do that here. Alright, so this should be close enough. This is great. This is our secant line through point P and point Q. Now, it has a slope, and we can geometrically determine that slope. So basically what we're doing is we're approximating the tangent line through P by making a secant line that goes through P and through Q. But this isn't good enough, is it? Because look at the degree of error here. What if this, especially, think about it, this function is kind of nice, but what if this were an exponential function? What if the x value of P were 5, or how about this? What if the x value of P were 1, and the x value of Q was, let's say, 5? Well, and we were taking a function, f of x equals 2 to the x, or something like that. Think of how much of a difference in y value there's going to be between P and Q with a tiny x shift of just 3 or 4 points. It's going to be absolutely astronomical. So you can see right off the bat why approximating this with a secant line is less than desirable, because the approximation of the tangent of the point that is tangent is going to be sometimes okay, but sometimes absolutely terrible, and most importantly, it's never going to be perfect, and we want to strive for complete perfection here. So what can we do? Well, let's not draw a secant line between P and Q. Let's draw a secant line between P and Q with Q moved closer. So what I'm saying is we can approximate the tangent line through P by moving Q closer to P on the function, which decreases our delta x. So if the limit is as delta x approaches 0, then we're going to get a tangent line through P with the slope that we've defined previously. So let's go ahead and do that. Let's move Q, and we'll leave this Q up here as it was, and just, think about it historically. And now let's move Q down here. So this is our new Q. We'll just call it Q2 down at the bottom. And let's draw another tangent line. We'll make this one yellow. Not another tangent line, another secant line between P and Q. Now look at this. Look at these two lines. We have our secant line 1 here that's red between Q for Q1, and it's okay. It's kind of close to the function, but look at the secant line between P and Q2. Because Q2 was moved closer to P, thereby making delta x smaller, the amount of error that we have between between this line, the secant line, and the line of the function itself is really, really small. The error has decreased. So let's go ahead and do another iteration of this. Let's move Q even closer. Let's have a Q3 here, and we'll draw another line, another secant line, and we'll make this one orange. So I'm going to draw a line here between, well, let's actually make a point Q3 first. So here's our point of Q3. Right there, Q3, and now let's draw a line that's, now look at that, it's nearly perfect once we draw a line between these 2 points. This looks really, really, really good. So as you can see, as we move our Q closer and closer and closer to P, our delta x continues to decrease in size. The smaller that delta x is, the smaller the area every single time. But there's still always going to be an error unless we make P and Q be right on top of each other. So if we have P equal to, well, we'll say like a QI, so P is equal to Q some iteration, and once we've done enough iterations of Q for it to be perfectly around P, then we know that a line that we draw that is tangential to this point is going to be just wonderful, because there's going to be zero error whatsoever, right? So what do we need to do here? Well, let's go ahead and look at this little point. Let's try and make this perfect, okay? Let's draw a line that is tangent to this point, which is what we really wanted all along. So I'll give a green marker here, and I'll draw a line that's tangent, and I'll extend it out a great way so we can see it. So this green line here, now this line is perfect. This line is tangent to that point. Let me change the color so it's a little more obvious. This line right here, it is tangent to point P. Therefore, between P and Q, because they're equal, the delta x is 0. So what we're doing is we're allowing the limit of whatever formula we're using to make Q closer and closer to P, we're allowing that limit to go to 0, okay, which will eventually make this 0. So what do we need to do here in order to arrive at this tangent line? How can we do this mathematically? Well, let's look at what we did and let's think about it mathematically. So for each iteration of Q, for each approximation to the tangent line that we did by moving Q and Q closer to P in order to decrease the delta x, here's what we did. Think about this. We went, first time we said, okay, the limit as delta x approaches 0 of f of x plus delta x minus f of x equals delta x. F of x plus delta x minus f of x is over delta x, over our change in x. Now look at this function and let's explain why it's perfect for an infinite number of iterations. Look right here at this point, our f of x plus delta x. We said that this corresponded perfectly over here with our point Q, our initial point Q. So we're saying point Q doesn't matter where point Q is to begin with. We have f of x delta x to give us our point Q. And so look at our initial equation. We have f of x plus delta x. So this right here, this part's just giving us Q, okay? But in order for Q to be equal to P, we need to subtract, well, f of x from that. So if we subtract f of x from f of x plus delta x, then that's going to bring this change of x, it's going to limit it to 0, right? Because we're limiting, we're evaluating it as the limit of delta x, so the change in x goes to 0. So this is going to get smaller and smaller and smaller and smaller and smaller and smaller, and therefore it will eventually go to 0. So the difference, the change in x, will be nothing if we go ahead and just subtract f of x itself from our f of x plus delta x. And if we leave all of this over the change in x, well, that just takes care of the x-axis, right? We've taken care of the y-axis by moving q and q closer to p, but we're doing that with respect to x and y. But as our x-axis value of q moves closer and closer to p, decreasing our delta x, well, then our y value is also going to move closer and closer to p. The closer and closer we get to p on the x-axis as we move q. So that's why this formula makes sense. So, well, this equation is nice, but delta x is kind of ugly, right? We understand that delta x is just the change in x, but when we go to actually start finding derivatives, we want to plug some stuff in, like if we want x squared, well, then here's how that would eventually end up looking. If we have, f of x plus delta x minus f of x, then we would have that for the function x squared, this is just a little aside here, for x squared, if we want f prime of x, then that's going to be equal to the limit as h approaches, as delta x, I'm getting ahead of myself, as delta x approaches 0 of x plus delta x squared minus x squared over delta x. Well, this delta x can get kind of confusing because we have another x here, and it looks like we're evaluating the same variable twice. So what's a good idea is to go ahead and replace delta x with something that's a little easier to work with. So I like to replace it with h. So as a little aside here, delta x is equal to h, and this is how I will use it in all of my future videos, okay? When we actually use the limit definition of the derivative to differentiate a function. So now with our new function, that's really the exact same thing. I'm just saying the limit as h approaches 0 of f of x plus h minus f of x all over h. This is the new function for the derivative, and this one is much, much, much easier to work with because there's no confusion as to, well, are we evaluating for x again, or what are we actually doing? So this new function is much easier to deal with. Now, let's go back to our original page. This is exactly what I promised I would allow us to arrive at and explain how we got there, that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all of that over h. This is the limit definition of the derivative. That's what it is. So by this token, can we not define the derivative itself without respect to the limit? Well, yeah, we can. We can just say that the derivative itself is the derivative of a function, which we can write as dx something, or f prime of something, or as d dx of something. Well, all of this is just the slope of the tangent line, or the slope of the line, I guess this is a better way to say it, tangential to any point on the function f of x. So that's all this is. Well, I shouldn't put that there. So that's all this is. This is the definition of the derivative. It's just saying I've got this point on my function. I want to know what the slope is exactly at that point, and I want no error whatsoever. Drawing secant lines gives us error, but drawing tangent lines gives us 0 error. And this is the equation for the tangent line. F prime of x is the limit as h approaches 0, or as delta x approaches 0, of f of x plus h minus f of x all over h here signifying delta x. And this right here is the graphical basis of the derivative. And of course, now your eyebrows may be raised here. Am I talking about the derivative at this point, or at this point, or what about this point, or this point right here? Well, the beauty of this is, if I want to take the derivative of a point on the function, I'll just get the slope at that point. But if I want a formula that will give me the derivative to any point on the function, well, then I can use the limit definition of the derivative, and you'll see this in future videos on this same playlist, the derivatives playlist for Cal 1, that I can arrive at I can use the limit definition of the derivative to arrive at a brand new function that will allow me to just plug in any x value I want and immediately arrive at the derivative for that specific point, and not have to completely, go in and relimit. Take the limit as h approaches 0 of everything again with this giant formula. So that's the beauty of this. That's the limit definition of the derivative. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is just telling us, as it says here, the slope of the line tangential to any point on the function f of x, or any function we're evaluating, be it g of x or e to the x or anything like that. So that's all there is to this.